Okay, we've started so people can join. Just for the join.
Okay, I see it now. Yeah.
All right, sorry about that. I'm back.
Okay, we've started the.
Sorry about that. I'm back.
So that people can join.
Started the. Sorry about that. I'm back.
So that people can join.
Started the. Sorry about that. I'm back. Oh man. Join.
Okay, that's. Okay.
Okay, can you hear me? Okay.
Yeah, can you hear me?
Yeah.
Okay, so we're good. I guess we're good then. We're just gonna let people join in.
If you want to learn some science, Malia, we're going to be doing a lot of science tonight. About, you know what a spectrum is?
Okay.
Oh yeah, I told you, right. Well, like, when you have a spectrum, you take some light, you put it through something that splits it up like a prism or a diffraction grating, and then you see lines in it. It tells you whether there's iron or hydrogen or whatever. So that's how we investigate. Real far away. Yeah, it's quite a tool. You can tell what's going on in the star. What it's made out of. You can also tell whether it's coming towards us or going away from us.
Okay. Yeah, if anyone is watching, then you can let us know by dropping it into the live chat.
Yeah, well, we've got 3 people watching. I don't know if that's you, me, and Scott, or who that is. But
Yeah, we'll see.
Went up, so it's got to be more than you, me, and Scott. Okay, Lynn and Chip. Okay. Good evening.
The pre-Halloween star party.
Yeah.
Yes, so we'll be zooming through the spectrum of the moon before we get started with the real stuff. What are we? This is a portion of the spectrum of the moon, which is basically reflecting the sun's light. So it's kind of in essence the sun spectrum that we're seeing through the moon's reflection. So we're going to be looking at some of the spectral lines in the sun spectrum, and after that we'll be getting into more peculiar objects. So it'll be starting off with the sun spectrum.
But the moon absorbs some of the.
Yeah, the moon does have an effect, but in essence, it's basically the sun's spectrum. So we won't be really looking at what effects the moon has, but we'll be basically the major lines in the sun spectrum.
Right.
They're labeled as Fraunhofer lines. Yeah.
So I was having a feedback issue earlier. Am I okay now?
Yeah.
Good. Yeah, so I don't know if everybody knows or not how a spectrum like this gets produced by the sun, but we could talk about that and just sort of explain what all this is. But the sun, like most stars, is this big hot ball of electrically charged gas that we call a plasma. And it's so hot that it's glowing, just like a stove burner might be glowing on an old coil electric stove. And it's giving off all the colors of the rainbow, plus ones we can't see. And all that light gets sent outward in all directions. But the sun has a cooler atmosphere, at least partly, around it. And those gases in the atmosphere of the sun, they absorb light. And what we've done here, I say we, it's not me, I didn't point the telescope, I shouldn't say we, is we're looking at the moon, and the moon, of course, shines by reflected sunlight. So we're seeing the actual spectrum of the sun, but reflected off of the moon itself, which is a pretty awesome thing.
Okay, well, just 3 more minutes before we officially start. So.
Yeah. So are there some dark lines indicate which wavelengths are absorbed by the moon?
Yeah, so each of these lines corresponds to a wavelength, and that corresponds to a specific element or compound that is absorbing that light on the sun's atmosphere. So we'll be talking about that, and just the major lines here, including the 2 big ones on the screen right now.
Yeah, and the moon has some effect on that too, of course.
Yeah.
Because the moon's not a perfect mirror, it doesn't reflect light 100%.
It absorbs some of the light, and it creates some interesting features. But for our purposes now, we're just treating it like the sun spectrum.
Absolutely. Which I think would surprise a lot of people to know that you could look at the spectrum of the sun at night.
Yeah.
And it won't hurt your eyes.
Exactly.
Okay, just have to quickly recenter the scope. Almost ready.
This is high drama of watching the spectrum shift.
Yeah, plus the scope's not tracking. It's tracking at sidereal, so I have to enter it.
Sure. So what that means is that the telescope that's creating this image is tracking at the same rate the stars move through the sky, but the moon does not move at that rate, and you're looking at a reflected spectrum of the sun off of the moon.
Okay, we got a few more.
Okay, well, it's 8 o'clock.
Well, we should give it a few, like maybe 2 more minutes.
Okay.
Our number of viewers is increasing right now.
It's still 8 o'clock, so Doug is keeping the time nicely.
Yeah.
Okay, well, hello there, Dash Martin. Okay, he teaches at Julian High School, I believe. Yeah, and good to have you back, Dash.
Okay.
I think he may be one of the few people on the faculty there that's actually got a telescope and getting into astronomy, at least that we know of.
Okay, I think we'll
Okay, Mike Teague's with us. Okay. Okay, well, I'm just going to make a few introductory remarks. This is Doug Solacey. I'm right now in San Diego. I'm not up in Julian, but I'm connected with everybody by way of Zoom. And tonight we have Scott Cardell with us. He's Associate Professor of Astronomy at Palomar College.
Hey, everybody.
Really glad to have Scott here. And of course, Vivek is operating a telescope in his backyard. He's got a 11-inch Celestron Cassegrain telescope with there's a picture of the spectrograph on the scope with a dew shield in case it gets humid. That will help keep moisture from condensing on the optics and spoiling the performance. So anyway, glad that Vivek's taking out an insurance policy tonight to keep things going. Okay.
Yeah, so I've got spectrograph here. It's much more, it's not the same. Last time we used a very small, low resolution grading. This one's going to be a pretty huge jump in resolution, and that comes with also a more restricted field of view in terms of the wait, that's the wrong one. In terms of the spectrum, but it's going to be interesting. Yep, I'm opening the wrong one. Okay.
Okay, and I just want to make a little announcement for people who maybe aren't aware. We just had a really momentous event happen in San Diego County this week. The County Board of Supervisors voted unanimously to institute an amendment to the light pollution part of the county lighting code that actually determines what lighting is allowed for new projects, and so this is going to be a very important thing. It's a dark sky friendly amendment to the county lighting code, and it was done at our request, and it was quite an event when they voted on it, and it's going to permit Julian to become an international dark sky community as a result, and also any other communities in the future in San Diego County that want to follow that path and limit light pollution and preserve darkness that we enjoy at night, helps us sleep, helps the wildlife, and certainly lets us look up at the sky and see great things. So anyway, just wanted to pass that on to everyone, and we'll be letting you know when we get our status as a dark sky community. We'll be submitting our application soon. And that's what made this possible. So we want to also thank you to everybody who helped make that possible.
Well, Doug, you've certainly done an amazing job spearheading at least a good portion of the work, and you and everyone else have done some amazing things. And I'm pretty sure that was the last thing that International Dark Sky Association really wanted to get that forward. So this is a big deal.
Yeah, it is, and we're working with actually part of the whole region of communities and also Zabrego State Park. We all kind of can join geographically, so this is going to be a whole big area that people can come out to and know that they can look up and see things that they'll never see in the city. It's also going to be good for the observatories, Mount Laguna and Mount Palomar, because it's going to help to preserve the natural darkness that they need to do their research, their scientific work. So anyway, it's been a work of a lot of people, including Scott. You helped.
I did almost nothing, but thank you.
You advised us and encouraged us. And Scott also helped shepherd Borrego Springs through the process 10 years ago when they became the first and only dark sky community in California. That will change, and will be the second, and hopefully there'll be a third and a fourth, and so on before too long.
Right, and to have two of them in San Diego County, in addition to Anza Borrego Desert State Park, is really quite an accomplishment for the area. And of course, the observatories appreciate that protections that are happening there, but it's good for everybody in the county and from surrounding areas too that want to come and check these places out.
Okay, well, I think we should probably get started with our with our journey today out into the cosmos.
Okay.
And we're not going to be so much looking at pretty pictures of the cosmos as we are going to be going deep into some of the stars and finding out what makes them what they are, what makes them, what kind of stars they are, and what are the processes going on in them. And that's where I'm going to kind of read into the background and let you guys take the reins, take us to where we're going to go.
Hey, let me give a shout out to Todd, who just joined us from Saskatchewan.
Okay, I guess we're ready now.
Yeah, did you want to start, Vivek, or did you?
Okay, yeah, I'll start. So, Doug already went over the equipment, so I guess we'll be looking at, give a preview of what we're going to be looking at tonight. So, we're first going to start off with the obvious, which is the moon, and because that's what it is, it's reflecting the sun spectrum, so we can look at the sun spectrum during nighttime by pointing at the moon, and that'll allow us to see some major spectral lines that caused by some very key elements in the sun's outer atmosphere. And we'll also be looking at another star that's quite famous, Deneb, and that's because it's a variable star with an interesting feature, and that's the same with the other object we'll be looking at, which is Gamma Cassiopeia, which is right in the middle of Cassiopeia. Let me turn on right in the middle of Cassiopeia. And then we'll be looking at a symbiotic star back in Cygnus. Then we'll be looking at analyzing blue shift on a star somewhere near Aries, and then after that we'll be looking at some chemically peculiar stars, including Alpheratz, which is a bright star in Pegasus and Andromeda. Then one final interesting star, which is a carbon star, which has an overabundance of carbon in Pisces. So we're first looking at some key spectral lines in the reflected spectrum of the sun.
So that's quite a variety of targets you've got picked out for us tonight.
Yeah.
And I know that for many people, spectroscopy is kind of a hard thing to perhaps relate to as opposed to pretty pictures. But I'll tell you that this is the thing that the professionals use to understand the universe, stars and galaxies and gas clouds. It's a super important tool for astronomers, and that's the main thing people are doing at the research observatories instead of just taking pictures.
Mm-hmm. So I guess we can start by looking at this particular spectral line. So we're starting. So basically, on the setup, I'm going to be starting from very shorter wavelength, more violet, more blue. That end of the spectrum, that's higher frequency, shorter wavelength, around 400 nanometers, and then we'll be going all the way to the end of the solar spectrum at around 700 nanometers and look at some of the particularly interesting features on the spectrum. So starting here, we have, if you notice on the screen, you have these two wide bands across the screen. That's calcium, H, and K. Those are the names of the spectral lines, and as the name gives it, they're produced by calcium. So I guess, Scott, you want to probably break that down for people.
Sure.
Yeah.
Sure. So the sun is, it's a star, and it's a big, hot, glowing ball of gas, and it's giving off all of the colors there are. But that light of the sun passes through its atmosphere, which is mostly made up of hydrogen and helium, but there are other elements in there like calcium. And as that light shines through these gases, it literally, photons of light, crash into individual atoms, and they knock into electrons and make electrons jump up to a higher level. And when they do that, they absorb light. And what you're seeing, this big array of these vertical lines there, are the absorption lines in the atmosphere of the spectrum of the sun. And of course, this is shining out on the moon, and the telescope is pointed at the moon and getting the spectrum of the sun by looking at the reflection of the spectrum off the moon, which is a pretty amazing accomplishment. Because there are these nice absorption lines from calcium, and it's one of the elements that's sometimes used to sort of isolate, zoom in on that and look for detail on the sun and its atmosphere that way. It's also done with hydrogen as well.
Okay, I guess I'll start moving the spectrum to a different part now. So.
Okay, can I voice a question?
Yeah.
I also encourage people who are watching to chat with us, let us know, where you are. But also, if you have a comment or a question, please don't be shy. Okay, what I was going to ask is, interesting that there are calcium lines. The sun, the process going on in the sun is fusing hydrogen atoms and turning them into helium, and releasing energy as a result. But how does the calcium get there if the sun's not producing calcium?
Yeah, so this was a big mystery for a long time, because when the first people were using spectroscopy to understand like what's in the atmosphere of the sun, what's the sun made of, they saw things like calcium and aluminum and iron and silicon, and they thought the sun was made of the same elements as Earth was. And it's not. So yet all of those things are there. So the cloud of gas that made the sun and the solar system was like 99% hydrogen and helium, actually slightly more than that, and less than 1% everything else. But that less than 1% everything else includes calcium and oxygen and aluminum and silicon and carbon and things like that. And so they are there in the sun because those elements were present in the nebula that formed the sun and the whole solar system, including our Earth. Thankfully, the nebula wasn't only hydrogen and helium, or else we wouldn't be here. That would have been bad. We would not be having this live event tonight if that was the case.
Okay, there we are. All right, almost got it. Right now, I'm just moving I'm turning a dial on the spectrograph to change the wavelength that you're seeing. So we're now approaching somewhere around 486 nanometers. So this is if you can see, obviously see the color, that's going to be a little bit teal. So I'm almost there. And there's a special wavelength at this part of the spectrum. You can probably already clearly see it because it's a pretty significant absorption line. Okay, I think that's good enough. So, all right. So this is hydrogen beta, and so this is a hydrogen line produced by hydrogen in the sun. So in a lot of stars, the most significant lines on them are hydrogen lines because our atmosphere is mostly made of hydrogen. So the most significant. So these are the entire series of these hydrogen lines that we see in the visible spectrum are called Balmer lines. So we have the longest wavelength, which is called hydrogen alpha. The second longest wavelength, which is right here, is called hydrogen beta. So that's one of the more significant features of the spectrum here. Is there?
Okay.
So
There's a question.
Question from the chat. Is there a contribution to the spectrum from the reflected surface of the moon itself? Yes. So because the moon isn't a perfect mirror, as Scott explained earlier, it's going to put its own imprint on the spectrum. And there's going to be some differences between what we see from the reflected spectrum and what we see from the solar spectrum based on what light the moon is absorbing. So that's a very interesting thing to look at, but for right now we're just trying to use the moon as a to emulate the sun spectrum, because obviously if I try to point this at the sun, then I'd destroy all of this stuff. So
Well, thankfully the Earth is in the way right now, so
yeah.
that won't happen tonight. But if, for instance, we were pointed at, say, the planet Uranus or Neptune, we might see added to that imprint that was just mentioned, absorption lines from methane that are in the atmosphere of
Yeah.
those planets.
In fact, in the last star party, we looked at the spectrum of Uranus and Neptune, and we saw that imprint from methane.
And so if you know what you're starting with, from the spectrum of the sun, you can compare the solar spectrum to the spectrum you're seeing from the moon or from some other world in the solar system, and try to pick out what's different. And it's work, but it's a doable thing.
Okay. Something significant here now.
Okay, we got someone Zen's from somewhere. Joined us. Okay. Okay, Elizabeth Denny. Okay. Hello.
So this here is a very significant feature. It's called the Magnesium Triplet, and that's because you've got 1, 2, and 3 very significant magnesium lines together. And these are very important for studying chromospheric activity, just like calcium, H, and K, and all of these other lines we're looking at. So this is basically this is the effect of magnesium atoms in the outer atmosphere of the sun absorbing light at this particular wavelengths, around 560, 580 nanometers, and this is the imprint.
Right. You mentioned that was from the chromosphere of the sun. So the bright disk or ball of the sun is usually what we call the photosphere, and the chromosphere is out above it, where you see things like prominences, big arches of gas that leap up from the sun and go back down. And so those magnesium lines are produced as light from those gases is absorbed at these wavelengths here from magnesium. I think that almost made sense. Did that make sense?
Hopefully, yeah. We have a problem. So, Doug, you were talking earlier about the 40-minute time limit.
Yeah, I just saw the little thing there.
Yeah. So I think we'll have to restart the meeting.
Okay, but that won't affect the YouTube though, right?
Yeah, just a small intermission while we try to figure that out.
Well, you'll be able to stay on. I think.
Huh?
It won't interrupt you.
Yeah, it won't interrupt me. You'll have to rejoin.
Yeah. Okay. You'll just have to create another party that we can invite us to it. Okay.
So, do we have time for me to answer this question that just came in from Dash?
Sure. Go ahead.
Okay, so basically these absorption lines, they're created in the outer part of the atom. So it's not isotopes, but it's electron energy orbital levels. And so magnesium, if I recall, is number 12, and it has 12 electrons. And what happens is, if you look at the outermost 1 or 2 electrons, they can jump up to a higher energy level when a photon hits them. And these absorption lines are produced as electrons jump up levels when they get smacked into by photons. So even hydrogen, which just has 1 electron, there are multiple lines from that, just because there are multiple places where those electrons could be. Hopefully that helps.
Okay, then that's not the same as ionization, right?
It's related. So when I teach this to my students, I kind of compare electron orbital levels to a ladder. And you could be at the bottom level, but if you add energy, you could be moved to a higher level. And if you add enough energy, you're no longer on the ladder, which would be the equivalent of taking an electron and moving it, hitting it so hard that it's no longer bound to the atom, and it becomes, the atom becomes ionized as that electron becomes lost.
Mm-hmm. So it becomes a free electron.
Right.
Okay. All right. difficult.
Okay, I think we'll have to restart Zoom now.
Okay,
Now
all
that we've
right.
answered the question.
Yeah, okay. Okay, so just create a new meeting and we'll just.
Yeah, I'll do that. Okay. Meanwhile, I'll just while they're trying to reconnect, while they're trying to reconnect, I'll move on to the next feature.
Are we back?
I think you're back.
I'm back, okay.
Okay,
That
well,
was-
let's.
Okay, sorry for the interruption, everybody. Since we are having a little tiny intermission, just wanted to say that, we would really welcome people's comments on the Star Party, on this one or any of the others, and you can give them to us by emailing us at juliandarkskynetwork@gmail.com. And we will read them carefully and respond and ponder over your comments and try to learn from them, okay?
Okay.
Is Scott back?
I am.
Okay, great.
Do we still have our audience? I think we do. Yay.
We do.
And of course, comments and questions in the chat are very welcomed as well.
Okay, I've got the next feature. This one's a very infamous one because this is the sodium doublet. So these are two pairs of spectral lines. It's caused by sodium atoms. In this case, this is these are sodium atoms in the outer atmosphere of the sun. But these two lines are also responsible for back when we used to have a lot of sodium vapor lights. These are the two strongest lines of sodium. So this is where we usually get a lot of light pollution. So if I were to say if I was in a sodium light polluted place, I could point this spectrograph into the sky and I would see these two lines appear due to these sodium vapor lights. So no matter what kind of sodium you've got, whether it's in the outer atmosphere of the sun, whether it's down here on Earth, or it's in another star, it's going to produce this feature.
Now, are those lines a problem for observatories that are doing scientific work, or do they just
if
them out?
I guess, well, the thing is, if for observatories, I guess the thing is for them, if they're trying to study the spectrum or in this region, it will be a problem. The other thing is sodium has some other lines out there too, so yeah, but
yeah, the chief advantage when low pressure sodium lights were being used was that they emitted very little light in the other wavelengths, and the astronomers basically were going to ignore this region right here because the sodium lines would be bright. And that was much better than the older alternative of mercury vapor lamps, which just had stuff everywhere. And so this low pressure sodium was a great choice for people in that regard.
Okay, we got a question from the chat. So the reason we know these are sodium is sodium, when you ionize it, when you heat it up, when you do anything to cause it to start emitting light, it will produce, due to the specific orbital structure of its electrons, it will start producing light at exactly 589 and 599 nanometers. So these wavelengths are. So when we look at the spectrum, if we see, okay, we've got this absorption line here at 589 and this absorption here at 590, that's going to be sodium. For magnesium, if we've got it at the wavelengths that correspond to the magnesium triplet or other wavelengths, and we can see the wavelength and calculate it to be, okay, it's this 500 something, then we know that's going to be magnesium. So due to how electrons are arranged in atoms, they're going to have specific wavelengths due to how they specifically jump orbitals. So the key thing here is the wavelength is tied to the energy, and electrons have a specific energy jump they make in atoms, and that's different depending on the atom. So a different energy jump corresponds to a different wavelength, and that's why we know if we see a line at 589 and 590, we can identify that as being from sodium.
Right, and we know they're 589 and 590 because Vivek has done his homework. He has calibrated his spectrograph. He also knows the lay of the land, so to speak, in terms of what are the main spectral lines that can be seen. These are things that people had to discover. But if anyone has access to, well, probably not, but maybe Dash, you do a diffraction grading. You could look at sodium light and see these two bright lines of color in the yellow kind of orange portion of the spectrum there, close together.
Okay.
Really pop.
Let me hold this open.
But you had to do some calibration before we could start tonight, didn't you?
Okay, so right now I'm just showing right now I have it set up, so I'm just showing the spectrum. So I just got here by just looking around for this pattern, and it's gonna be at around orange. So, but later tonight when we're actually gonna be trying to look at specific stars, we're gonna be doing wavelength calibration on the spot too.
Okay.
But for now,
Okay.
looking for the feature. I got this picture here from, I was talking about earlier about light pollution. So, and this is kind of going to answer Dash's question. So if you see in the background, you can see the correspondence from sodium vapor light pollution. It's really faint, but hopefully you guys can see that. And then we've got here, if you look at these very tiny notches right here and right here, that's sodium on a star called Anilam. I don't know how to pronounce that, but
That's okay.
if you notice, they're kind of offset. So that's the redshift that we're talking about because the star is moving away from us. So
Nice.
think of this light pollution as being the rest wavelength from light from Earth, and we can think of this being as what the star is doing. So that offset is the amount of redshift. So yes, well, the wavelengths change with redshift. So you have to do kind of do pattern recognition. So like if you have a really redshifted source like a quasar, then you have to look at the patterns of the spectral lines to identify, oh, this is the specific Lyman alpha or whatever wavelength you're looking at. That's the wavelength that we're seeing here.
And that's an interesting thing that you mentioned, because when quasars were first discovered and people were looking at the spectra, they looked and they saw nothing that they recognized. It was just really blowing everybody's minds. It's just like, they didn't get it. And it was Martin Schmidt at Caltech, who had been using the Hale telescope at Palomar Observatory, that realized he was seeing the familiar lines of hydrogen, but they were redshifted so very far that nobody recognized them as such. And that meant that this was an object that was super far away, and the expansion of the universe was shifting its light further and further to the red and shifting those spectral lines further and further to the red. And it wasn't until I recognized this familiar pattern in an unfamiliar place that all began to make sense for people.
Okay, I'm trying to get to hydrogen alpha now. It's going to be the final one we look at before we start going beyond the solar system. If I can get there. Let's see.
Yes, looking at the question, each chemical element does have basically exactly like a barcode, and it is unique to that. Molecules as well. And when the whole thing gets shifted from a red shift or even a blue shift, that whole barcode gets shifted towards the red end or the blue end. That's exactly right, Dash.
Okay, this is hydrogen alpha now. This will be the star for a while. So this is caused by hydrogen in the outer atmosphere of stars, just like hydrogen beta, except this is hydrogen alpha. So it's the longest wavelength that we can see visible light from hydrogen. So it's a very important wavelength to a lot of people because this is what normally if we take a picture of a nebula, most of that emission nebula full of hydrogen, most of that light is going to come from this particular wavelength, hydrogen alpha. So this is a very important wavelength in astronomy because it comes up a lot, and here we can see it present on the spectrum of the sun.
Right. So if you've seen a picture of the Orion Nebula, there's a lot of red in there, and it's coming from this.
Orion Nebula? I think I have something for that.
Oh.
We got the red here.
Yeah.
See all this red gas. That's hydrogen alpha.
Except in a nebula like that, the spectrum is sort of the opposite of what we're just seeing. It's glowing with that red color instead of absorbing it. But it's all coming from hydrogen gas.
Instead of the hydrogen absorbing the light coming from within the star, it's being excited and it's emitting the light at those wavelengths. So that's
just
yeah.
I was gonna say, just like you see in like a neon sign,
yeah,
or a sign that might say vacancy.
Yeah. Okay.
Yeah, just kind of add something. That particular object, the Orion Nebula, is something that you can see in binoculars. You won't see the colors, but you can see it in Orion's belt. So encourage you to go and check it out live in person. You don't need a telescope or a spectrograph to see it. And then you can kind of think, well, it's a big cloud of hydrogen gas emitting light as ionized.
Okay. I think it's...
Yeah, it's the middle star in the sword.
Yeah. Oh, the sword, right. Thank you.
Yeah.
I think it's time we go extraterrestrial now.
All right, so what's going to be the next target?
Deneb.
Deneb, all right.
Okay, so we'll keep this looping, but I'll get out of...
Right now, you're gonna be slewing your telescope, right?
Yeah, we're gonna... Yeah.
And Deneb is another target you can see very well without binoculars or anything, because it's one of the stars in the summer triangle. Right.
Yeah, Deneb's the 19th brightest star in the night sky, and it's a star that's much bigger than the sun, much more luminous than the sun. We're not exactly sure how far away it is, but it's on the order of 2,600 light years, which is kind of astonishing because Deneb's a really bright star. In fact, all of the stars at night that are brighter than Deneb are brighter because they're closer than Deneb. So like Deneb is bright and it's far, which tells us it's a really luminous star. Possibly like around 200,000 times the luminosity of the sun. So that means every second it puts out 200,000 times more light energy than the sun does. Don't think you'd want to be on a planet next to that.
Quick addendum, I forgot that I have to switch camera before I can go to Deneb, so...
Okay, so I should tell people more things about Deneb then, is that it?
Yeah.
Okay, so it's about 19 times the mass of the sun. It's what we refer to as a supergiant star, and that means someday it will explode as a supernova. I'm thinking maybe like just before the election. No, actually, no, we don't think it's going to be anytime soon. Not likely. And an exploding star the night before the election. Yeah, never mind. Let's not go there. So, yeah, it's a pretty amazing star. It's the brightest star in the constellation of Cygnus the Swan. And okay, so the question is, how do we know the mass of the star that far away? And assuming you know the distance, and we kind of do, so our mass estimates and luminosity estimates are going to be off a bit.
Okay.
But if you know the distance, then you can very definitely determine the luminosity just by looking at how bright it is in the sky versus how far away it is, because we know how things fade with distance. So determining the luminosity is not that hard. And then there's a direct relationship between the mass of the star and the luminosity of the star. So it's literally like people have made this graph of mass and luminosity for many stars, and there's a pattern that's there. And that's all you need at this point. But before that, we didn't really know the mass of any star except the sun. And the way that you determine the mass of stars from the very beginning is to find binary stars, two stars that orbit each other. And then you can play with Newton's equations of gravity and Kepler's third law and do the math to determine the masses of the objects that are orbiting each other. Maybe that was too long of an answer.
That's better.
It wasn't too long for me.
Okay. Yeah, so having binary stars has been super useful for us to be able to determine the masses of stars. And oh, yay. It has been fortunate that there is a direct relationship between mass and luminosity, so that if we have a way to get distance, we can get luminosity. And because those mass and luminosity are interlinked, then once you've got that, you've got the other.
Yeah, that was a good question.
Yeah.
Okay.
I just want to say that those kind of questions, how do we know? Those are always good questions.
I can finally go to Deneb now, for real.
All right.
I had to change from a color to monochrome camera, just for processing purposes.
Oh, you had to switch cameras.
Because the other one was a color camera.
Okay.
So I don't want to have to do I don't have the pipeline for debayering and all of that.
Okay. Folks, he's working really hard here for you, and I hope you all appreciate that. This is, especially on the fly like this. Out at Palomar Observatory, if they were going to switch cameras during the night, which they can do, it does take a few minutes, and they have to rebalance the telescope and move secondary mirrors in and out, and it's big work for the professionals, and it's big work right here too.
I have the convenience of the cameras being basically the same thing. They're just different sensors.
Excellent. Hey, it's a star.
Yeah.
Just got to get it on the slit.
That's what I was just going to say. That looks like you're moving it towards the slit right there. Basically, we want to get just a little bit of the light of the star down to the spectrograph. And so he's lining it up there on the slit.
Okay. No, that's a little too far. Okay. It's a careful balancing act. They're trying to not then have to start guiding once it's done. Okay. Now it's gonna track on this star so that we stay on the slit and we get
The one in your little square, right?
Yeah.
Is your guide star. And so the computer is looking at that image, and it's talking to the telescope and helping to keep our star centered on the slit.
Okay. All right. So now we're gonna take a spectrum and save it, and then do some additional processing, and then we'll spit out our image, and then we can talk about it.
Yeah.
Okay.
So-
We've got a chat question. How are we able to tell when the star will explode? I think she's talking about Deneb, probably.
Generally, we're not. I was joking when I mentioned, right before the election, we know which stars will explode, or at least a handful of the ones that will. stars that are much more massive than our sun all end up by exploding, creating a supernova or some variation of that. Deneb is around 19 times the mass of the sun, and it'll do that. The trick is that while we can see the outside of the star and the atmosphere of the star, and we'll see details of that in its spectrum in a moment, the real determination of what's going on is happening deep within the core of the star. And it's kind of like, we know there's going to be a big earthquake in LA someday, and we can determine the odds of it happening in like the next 100 years or something like that. We can determine the odds of this happening for Deneb nowhere near as precisely as we can for earthquakes. And we have no idea when the next big quake in LA will be. But we know that Deneb and stars like it will explode. And we know that stars like this live for mere millions of years, which sounds kind of wrong. And the reason I say mere is because stars like the sun will live for billions with a B of years, like 10 billion years, whereas a star like Deneb here might do this for just a few million years.
Okay.
So hopefully that helps.
Here's a this is what I'm going to use to calibrate the spectrum of the star. I'm going to use this to calibrate it so that we can get each pixel assigned to each wavelength so that we can get a good spectrum. So we're doing that.
So where are those lines coming from?
That's an argon neon lamp in the spectrograph.
Ah, right. So within his spectrograph, he has some lamps that emit known wavelengths of light. And so he basically is using that to calibrate his spectrograph. This is exactly what everyone does at, say, Palomar Observatory. Basically, up there, the astronomers will take spectra of lamps in the spectrograph, usually late afternoon before they go to dinner, and run those calibrations and then come back and observe for the night. You might even do again during the night just to see if the instrument has changed at all. And so he's doing the exact same thing here so that we'll know which spectral lines we're looking at when we look at Deneb.
Okay, we have a chat question from Dash Martin, kind of on this topic, which is always a hot one.
That's just fun. Oh my god, I did it wrong.
So,
or actually, this is not
yeah,
but kind of spinning off.
We can look at stars and we can measure their outer properties pretty precisely, and we can, like temperature and luminosity and size, and compared to like people, stars are relatively simple things because it's all just temperature and pressure and gravity and things like that. And literally what people do is they build mathematical models of a star at certain depths within the star and see how well that produces what we really see out in the outside world. And so the main way for us to initially know about the interior of a star was through mathematical modeling. There's now a thing that maybe you've heard of called, well, when it's applied to the sun, it's called helioseismology, but also there's a stellar seismology too. We can, with some stars, see vibrations that reverberate through the stars. And just like seismic waves passing through Earth tell us about the core of the Earth and the mantle of the Earth, we can see waves that pass through stars that tell us about the interior of the star too. That's much newer, but it's absolutely a thing that people do. And it looks like we've got some results here, huh?
This is a 30-second exposure of the spectrum, so it's a little noisy, but I guess we can get the gist from this.
So what's that big dark line?
At the center?
Yeah.
That's hydrogen alpha.
Okay, and it's offset.
Right now looking at hydrogen alpha, it's particular. that region on Deneb. And this is where we can see a very special profile of the star. And we designated the P Cygni profile because what we have here essentially is we've got this normal absorption line here, but at the same time there's a little bit of emission of hydrogen over here, and that's a profile caused by the fact that the Deneb actually pulsates, and that there's an expanding lobe of gas that emits that has hydrogen, so it emits light, and what we see here is absorption from the star itself and emission from that lobe of gas, which is what we can see right here in this part of the spectrum over there.
Right. There you go, that spike right there.
It's a little noisy here, but this is what you get with 30 seconds of exposure. But because this is a variable star, we can actually compare this with previous data and see how the spectrum changes. So let me pull up a spectrum taken a few months ago. Let me get that.
So he mentioned that it's a variable star. That literally means this is a star that changes its brightness. It's not a huge variation, as I recall, but it is a variation, and it is produced by a physical pulsation of the star itself.
So we can compare this now. So if we compare this profile, so this is obviously a lot more data taken, more than 30 seconds, but we can see how this star has evolved over this. We can see how the star is different from how it was 3 months ago in terms of the profile. So the emission is a little less strong here. So the profile's actually changed based on its pulsations. So if we continue monitoring the spectrum, we can get a lot from understanding what the structure of the star is. So a spectrum of a star, for some stars, it's a dynamic thing. The spectrum is always changing. So, and that's true for Deneb. Due to the fact that we have this expanding lobe of gas caused by Deneb's instability that produces these pulsations.
So okay, I think you just answered Dash's question, what causes that pulsation? I don't know if you want to add to it.
So the pulsation is... Do you want to answer, or...?
I can say something about it, but maybe you know more.
Okay, so the pulsation, Deneb is part of its own variable star class.
Yeah.
When we talk about variable stars, we always have there's usually a prototype that we base a class off of. And
right.
Deneb is the prototype of its own class. These stars are called alpha Cygni variables because Deneb is alpha Cygni because it's the brightest star in Cygnus. And these stars are pretty large. And they have some instability to them because they're pretty massive. So that allows a lot of these stars to have variability that produces these pulsations. And what this usually means is we have it's kind of like if you have a little knowledge of thermodynamics, or like a heat kettle, you can have gas that expands, contracts, and that kind of mechanism, which we call the kappa mechanism, that causes these pulsations to happen in these stars. And these pulsations can release gas, and what we're seeing in the spectrum is that release. And it's a dynamic process, so that this is always changing. So we can see how this was today and how it is a few months ago.
So the nice thing is we do not live next to a star that pulsates. Imagine if the weather forecast was not only like temperature and whether it's going to be cloudy or raining or whatever, but whether we had to go into our shelters or not because the star was going to expand and get hotter. So it's good to live next to a star that does not do that. And the sun is in this state of balance between basically gravity that's trying to squeeze and compress it, and then the nuclear fusion reactions at the core that are and pressure that's just pushing back the other way. And it's in a state of balance. And in some stars, that reaction at the core sort of heats up, and that will expand, literally physically expand the star. But that process can cause it to cool, which means it falls back inward. And you can get pulsations produced that way.
I'd like to point out something I just realized. If you pay attention to the graph, the y-axis, you can see the relative flux here is around 0.8. So this is not a, this is like a 20% dip over here. But if you look at this spectrum, this is a 40% dip. So this is actually, right now, this is much different compared to what this is right now. So
that's cool. Because I'm a cheater, I went to Wikipedia, so I hope that's okay. And there are actually 16 different harmonic pulsations that Deneb has. And so there's different things all working away there. And sometimes those will like co-add to make bigger differences here that we'll see in the spectrum or with velocity of gas than other times. Sometimes they kind of dim each other out a little bit. But it says that these pulsation modes have periods that range between 6.9 and just over almost 101 days.
Okay, I think
it's very read out.
Yeah. So there's an interplay of different processes going on within the star.
So yeah, Dave, yeah, these are both hydrogen alpha related. These are both. And the difference in lambda is because of redshift and blueshift. So if you look at the right, we can see that the expanding level of gas is coming at us because right in our context, it's coming away from us, while the star has overall, it has this part is blue shifted over here, while the emission part is slightly red shifted. So from our perspective, this gas, the expanding level of gas, is receding from us. And that's so yeah. You just have to consider perspective when you look at these graphs in terms of how we're looking at the star to understand red shifts and blue shifts. We have another warning from Zoom. I think you saw that.
No.
Oh, do we?
We'll have to do the same process again of restarting the meeting. And I guess while we'll do that, I'll change target. So
can you change the length of the? Oh, I see. It says we have 8 minutes left. Can you change the length of the?
In order to make the cap longer than 40 minutes, we have to pay money. So.
Oh.
It just started doing this now, only today, during the star party. Before that, it allowed us. So.
Yeah, we went 2 hours before with no problem, but yeah. Okay,
So,
well, I guess Zoom caught up with us, okay.
I guess I'll change targets then while we're restarting the meeting.
Okay, yeah.
Okay, so hang on, everyone.
Watching.
We'll still be here, and we'll answer Madison's question after we hop back.
Yeah.
Yeah, and you won't lose Vivek, you'll just lose us for a couple minutes or a minute.
Yeah, Doug and Scott are leaving.
This is silly. I do this part again. Okay. So, is anyone back?
So are we back?
I think we're back, right? Oh, no. Todd, I'm still here. Even if they leave, I'm still here. Just remember that.
Okay,
My
I'm
laptop.
back. Can you hear me?
Yes.
Yeah. Yeah, just
Vivek, can you hear us?
funny in the chat.
I think we need to kick Todd out of the chat.
I'm watching.
Todd, by the way, I'm very jealous of him because he can see awesome displays of northern lights from his house
Huh?
in Saskatchewan.
Oh, really? Okay.
Yeah,
Well,
but
thanks
he
for-
has to pay the dues because he also has to deal with the temperatures there.
Yeah, okay. I say we can reconvene there next summer.
Okay.
Yeah, but you won't see northern lights in the summer.
Oh, okay. So you got okay.
We've
You
got
got
a little
to
bit
dress
of low
appropriately
line.
and be motivated.
Right.
Okay.
In my one expedition, well, up to Alaska, was told there's no cold weather, there's just bad clothing.
And it's snowing right now. Okay, so he says the sky is awesome, but it's also snowing. I guess it's not awesome at this moment, though, or it wouldn't be snowing.
Yeah, so Madison had a question. Do you think we could predict future graphs? And I think the answer is yes. I mean, that's because people have done the work to see that there are these different harmonics reverberating. Wow, I can't speak anymore. Reverberating through the star. It takes some real work to do that, and it might not be possible with the equipment we have here. It might take bigger telescope with some more detail to be able to pull that out. But people certainly have done that kind of work.
Can I interject about
and
that?
should be able to see how things change in the future. Now,
Yeah,
what's
so-
our new target?
Yeah, we're going to Navi. So I just want to quickly talk about the graph.
He's probably
Oh,
dep-
he's busy.
with the equipment.
Busy.
It's
pointing.
slewing right now.
Yeah,
You didn't-
I
you
just
didn't-
want to say, if you noticed that on the right-hand side of the screen a little while ago, there was a massive
Oh.
amount of.
I just realized it was unmuted.
Oh, okay.
Okay, so I want to mention about the graphs. Well, it depends on the variable, because if you have something that's very inconsistent and it's inconsistently variable, then you can't predict it. But if as I was talking about, if it has those harmonic modes, we can study that. And actually, the spectrograph I'm using right now for doing this was built to do precisely that.
Oh, excellent.
For a type of star called a BE star, which is what we're going to right now, which is called Gamma Cassiopeia. It's a BE star, and this is actually the type of star this spectrograph was built to analyze, so that'll be interesting. The only limitation is I have to scroll down to N on the hand controller, so.
Okay, take a little bit. Yeah, I was mentioning about all that gobbledygooky language that was flashing by a little while ago. That's actually the script that Vivek had to write in order to do this kind of stuff. He had to create a whole, script of, or code to tell the computer what to do with the data. So that's part of the project of doing this. And I don't know how long that took.
Yeah,
I think
it's a Python script. So if you know what Python is, it's a language, and then you can use that to use libraries to process data. So that's what I was using to.
I was going to ask how long you've been working with snakes, but I guess that's not the right question then.
Yeah.
Sorry.
Now I have to get Gamma Cas on the split now.
So Gamma Cas is also called Navi,
Yeah.
and it was named by Gus Grissom.
Oh yeah, I remember.
Yeah, and because Navi, his middle name was Ivan, and Navi is that backwards. And it was a star that the astronauts used for navigation purposes.
Oh,
The middle star in the W of Cassiopeia.
okay. Wow.
Strangely enough, that star is a pretty prominent star, but it didn't have a proper name.
What happened? The Greeks didn't notice it, or the Arabs, or
I don't think so.
Athenians? Or...
Well, at least not one that people used out here in the West.
I think people can already see what's special about the star. If you see this part of the spectrum, it's a little bit brighter than the rest. So that's a little bit about what the star's like.
Noticeably.
Just let me take a 30 seconds. Yeah. Maybe I'll take a longer since the last spectrum was a bit noisy.
So this is another star that's bigger than the sun. It's about 17 times the mass of the sun. It's estimated to be about 34,000 times the luminosity of the sun, and it's about 550 light years away.
And it's in the W of Cassiopeia, or the M, depending on, or the 3 or the E, depending on where it is in the sky. It's one of those stars, right, that forms that basic asterism.
Yeah, it's a part of the W of Cass. I think it's the
Right.
middle of it, right? It's right in the middle.
Yeah, it is. And asterism's a good word for that, yes.
Yeah, so that is something you can spot with your binoculars. And if you have a star chart or a planisphere, you can identify it precisely and then take a look with your binoculars or just your naked eye and see it.
So, okay, there we got a good spectrum, so now I can actually...
We'll find out what's weird about it, right? It's not an ordinary star, right?
Yeah, it's a BE star. We're gonna talk about what that is once I rename this thing.
Right. When we say ordinary, we mean main sequence, like the sun. Majority of stars are like the sun, but many aren't.
Yeah, so the fact that it's a B tells us some things right away. I mean, the stars are classified by spectral types, O, B, A, F, G, K, M, and the sun is a G. And the O stars are the hottest, and the Bs are the next hottest. But the fact that there's this E in the spectral type is, well, tells us that there is something interesting going on there. I don't know if I want to give it away, so.
Yeah, I'm just right now typing in the wavelengths for the calibration. So. Sick. And also there's a dog.
Also referred to as gamma Cassiopeia or Cassiopeia. The stars are in the constellations kind of mostly named alpha, beta, gamma by brightness. So gamma would be the third brightest star in the constellation of Cassiopeia.
Okay. No, wait, this is a...
Okay.
Okay, I did the wrong thing, but I think... Okay, now it's working. What? Okay.
This star has spooked the neighborhood dogs.
Yeah, it has. Definitely.
So another question from Dash is, yes, there are absolutely absorption lines and emission lines outside of the visible range of the spectrum. Just because we only see this narrow range of the spectrum doesn't mean that doesn't happen elsewhere. And one of the reasons, there are many actually, why we do astronomy from space is many ultraviolet lines and emission lines are absorbed by Earth's atmosphere. Thankfully, we have an ozone layer that absorbs a lot of the ultraviolet, but as you probably know, water, vapor, and clouds absorb infrared. And so we do a lot of astronomy from high mountaintops, but there are absolutely absorption and emission lines outside of the visible range of the spectrum. Even in the radio portion of the spectrum, and there should be some at higher regions in the spectrum, higher energy regions of the spectrum too, like even into X-ray and things like that.
Okay, I don't know what's going on here, but something cooked out, but let's look at this. Okay, now something definitely cooked out. Interesting. Okay, anyways. Let me get something else for that.
It's an exact science, folks.
Well, yes, everything's an exact science. Let
The dog seconded that.
Yeah,
Let me just.
I
Oh
played
my
the
goodness,
dog.
the dogs. Anyways, this is what. If everything worked out, this is what it would be looking like.
Oh,
So
so you shot this earlier?
yeah, I shot this last year, but I don't know why. Also, the dogs are cooking out, but yeah, something went wrong. But I'll just talk about this since this is what we're just looking at. But
Yeah, this definitely looks really different from what you've shown us before.
yeah, so you can see this bright spot here, and that's exactly what you see here. You just got this big giant emission line of hydrogen. So this is still hydrogen alpha. And the reason is that is similar to Deneb, but in a different way. It also has an expanded lobe of gas, and depending on the orientation, we get different results of how that star looks like. And this is a BE star, so the E refers to emission. So that's what we have here is an emission line. This is from that lobe of gas around the star, emitting light, and we can't even see the absorption from the outer atmosphere because it's completely flooded by this emission by the star. Another example of this, if we look at here's what it would look like if you're in a different orientation of that lobe of gas. We would see two spikes, and that's because if you have a lobe of gas, you're gonna have one left of the star, one of the right of the star. So we can get two spikes depending on the orientation of the star. And this is the particular interesting thing on BE stars, is this feature.
So we think that this particular star is a star that is rotating really fast, and that there is gas ejected out from it, and that's this hot glowing gas that he's detected here with this emission line. Gas that used to be part of the star that has been flung outward.
Yeah.
One of the things for these stars that rotate really rapidly is they're not round spheres like the sun is. They're wider at the middle. Like I'm kind of wider at the middle too, but not because I'm rapidly rotating.
You're not rotating fast.
No, there are other reasons, other factors. But these stars are rapid rotators, and that makes the equator extend outward pretty dramatically.
No, kind of like, I guess, Jupiter, right?
Jupiter's that way a little bit. Earth is, wider at the equator than it is at the poles. But this star, I forget what its rotation period is. I'll have to see if I can look it up.
Okay. Well.
So it's rotating at 432 kilometers per second.
Yeah, that's.
Okay.
It's not a starring a slowpoke.
What's that?
The star isn't a slowpoke.
Thanks for sharing that, Todd.
I think, yeah.
Okay. I think I have an idea of what went wrong with that graph, so hopefully the next target doesn't have that problem.
Are you slewing to the next target?
Yeah.
So what is that?
This one is CH Cygni. It is a symbiotic star.
Ah.
Very interesting type of star.
Does that mean there's another star involved with it?
Yeah.
Okay.
We've got basically a red giant involved with I think it's a smaller white dwarf, if I
Yes.
remember. Yeah.
Yes, it is.
And I think it's right there on the screen, so I can just get that.
Wow, is that the one we're seeing? Oh, look at that.
Come to the slit.
Actually, you resolve the two stars there. What you're talking.
What did he say, Doug?
I said the two stars are resolved, I believe, right?
No, they're not.
Oh, they're not. Okay, well we see.
That's just one star. If you're seeing other dots next to it, That's an artifact of the off-axis guider on the spectrograph.
Oh, okay. All right.
The optics on the off-axis guider are a bit wonky, so.
Yeah. Okay. Well, okay. Could have fooled me, but
See, that's one of the values of spectroscopy here, though, is that when you point a telescope at a star and you see one, a spectrum can sometimes tell you that there are two in a variety of different ways. These two stars, as you mentioned, there's a red giant and a white dwarf, and they have a 15.5-year orbital period. And cool things are happening here. Should I say what they are?
You should, yeah, I guess, because the spectrum doesn't really show it on face value, so I think it's good to introduce it.
So when you have a star that's a red giant star, they're kind of big and bloated, and the star has expanded, and some of the outermost layers of the star are not really held on to each other very well. And in this particular case, where we have two stars here, we have a white dwarf as the other star, and it's a small kind of compressed thing. And what can happen is gases from the red giant star can literally be pulled off to the other star and start what we call accreting down onto this other star. We'll usually get a wide, like a flat disk of gas in orbit around the white dwarf. The same kind of thing happens around a black hole or a neutron star too.
Yeah.
Go ahead.
Are you answering Todd's question?
I didn't. I was just talking, but I just see Todd's question there now.
I'm going to answer it with some graphs.
Okay.
So let me see if I can find a good example. So this is the good example. Combined with spectrums. Okay, so this is the magnesium triplet from earlier in the evening when we saw it on the reflected moon spectrum. So this is from CAF, which is no, not from CAF. This is from some star in Canis Minor, and we can see a very nice and sharp presence of the spectral line. So when you have a very rapidly rotating star, what can happen is it starts to get blurred out. So because of the Doppler shift from the star rotating, when you have one side going away, one side coming towards you, that Doppler shift can cause Doppler broadening, where the spectral line gets broadened and you get a much more it's a bit larger width, and it becomes a little more diluted. So that's the presence you get here with this star, is because it's a very, very rapidly rotating star. So the spectral lines start to become a little more fuzzy, quote unquote.
Yeah. Now, if for some reason this star was like really big in our sky, which of course it's not, and you could look at one side of it and then look at another side of it, you could see if the orientation was right, like a red shift on one side or a blue shift on the other. And that is the thing we can measure for rotation of planets, or that the Hubble Space Telescope has done with accretion disks around a black hole at the center of other galaxies, to see one side is spinning one way. So, you see the other question?
Yeah, I saw it. I need to find some. I have a graph on this also, so I'm gonna try to find it.
We can theoretically, for things, we can measure rotation rates of a wide range of things. When we're talking about in an accretion disk, which is a spinning disk of gas around a thing like a white dwarf, like we hope to see here, or a neutron star or a black hole. In some cases, these disks have matter that's spiraling around them at a considerably high fraction of the speed of light. Like gas spiraling around a black hole is going just outrageously fast compared to light speed.
I think this is a suitable graph. So hopefully I can explain this graph a bit. So on the left, we have apparent rotational speed. So what we measure based on looking at the spectrum, what the rotational speed of the star is. And here's a measure of broadening of that line. So when we're talking about these stars I was looking at earlier, these were on the order of 52 or around 180 kilometers per second. But as we saw with Gamma, Cassiopeia, or Navi, they can go even more insane. But one thing to keep in mind is this is apparent rotational velocity. The thing is, we don't know what way the star's axis is pointed. We can only guess the velocity we see, but it could be a little less
Oh,
than it actually is,
we lose
just
your
based
audio?
on how we're looking at the star. Yeah? Were you saying something?
Are we losing his audio, or am I having audio problems?
Okay,
No,
you're clear. You're clear now.
No, we were having a hard time hearing you, Vivek. We lost you for about 20 seconds.
Okay,
Maybe
don't
you
need to. What was the last thing I said?
So you were explaining that when something is rotating, we don't know necessarily what the rotational axis is, the way it's pointed.
So if it's
So there's a lot of uncertainty based on that, and it could be a lot more or a lot. Well, go ahead.
if it's like 45 degrees oriented from how we're seeing it, then what we're seeing as rotation is a lot less than what it actually is. Because the Doppler shift is slightly less because we're not seeing that rotation head on. So that's why this particular axis is called v sine I. It's basically apparent rotational velocity based on an angle I, which we don't actually know. And v is the actual velocity. So it's basically dependent on the angle of this axis is, and we don't know that for a lot of stars. However, for some stars, we're able to actually find that out using a variety of techniques, but usually when we look at the rotational velocity, it's mostly apparent.
Yeah, the same thing happens when we use spectroscopy to find planets that orbit other stars. That gives you some upper limit as to what the mass of the planet could be, but you don't really know what it is because you don't know the angle of the orbit. It's the same kind of thing.
Would you be able to get any clues if you rotate the camera or, I don't know, rotate, the spectrograph?
No, he would have to like warp to some other part of space and look at it from a different angle.
Okay.
He could jump about 10 light years, east.
Yeah.
Hop out.
Or north
It's
or something like that.
the perspective of Earth relative to these stars. That's basically the crux of it. Okay, so I'm gonna have to now rerun this amazing program again.
Yeah, the thing about these Doppler shifts is it only tells you what's going directly toward you and directly away from you. And real motion is never quite just that, usually. Something is either going purely at you or purely away from you. There's usually some kind of angle involved. And so that gives you some limitations as to what you can measure sometimes. So Vivek is still running his script there, and hopefully we'll see something cool here.
Well, if you already see the capture program, we can see some interesting things going on, but they're not very clear yet.
Oh, another question. So with the pulsating star, does rotation speed up and slow down similar to a spinning figure skater? I believe so. How's that for a bad answer? I know that when a star goes like dies and goes through its collapse to form something like a neutron star or something, they speed up tremendously for exactly that same reason. It should be an effect on the rotation of a star, but a star can get a bit complicated because it's not a solid thing.
Yeah, this is getting some complicated stuff and simulations and stuff. There's a lot of work being done on this part.
Yeah.
It's very interesting stuff, but it's also complicated stuff. But yeah, this is like in the realm of computer simulations where we have to look at how a fluid, it's like, it's not a solid, so it's not rotating uniformly. Just like,
right.
And then we have differential rotation, radial rotation, so it's a more complex field for sure.
Yeah, exactly. But generally speaking, as something would contract, rotation would speed up, and as it expands, it would slow down. Is there like a drag effect as well? I'm going to say I don't know.
Drag effect of what?
Like friction.
From friction from what?
From within the star, I assume.
From the fluids themselves? Yeah.
Or maybe a gravitational.
Yeah, a fluid interacting with the fluid will have some sort of friction, of course. That's one part that makes it a little more complicated too. Hopefully this doesn't bug out either. Get a nice spec. Come on. Okay, I think this program doesn't really like emission line stars, so let me just get a backup plan for this. So many windows. Okay.
Like Roger's signing off. If he's still there, thanks for joining us.
Yeah, Roger's from Borrego Springs.
Yeah, there's this other program that it won't be doing the wavelength calibration, but it'll be enough for us to talk about it. There's the spectrum.
So basically you're changing the scaling on the graph, right?
I'm just focusing on just the spectrum. That's what I'm doing.
Okay. Oh, and lo and behold, there's something quite interesting going on there.
Here we are. This is our 2 emission lines. A pair of emission lines for us. The spectrum's pretty noisy because, this is a pretty fainter star, but we can already see it in here, and we're just seeing it here in graph form. So most of this little spiky stuff is noise. We can clearly see this distinct peak over here, distinct peak here, and that's the emission lines from. Those are 2 different emission lines from the constituents of the system.
So recall that, just for people listening in, this is a system that's a red giant and a white dwarf, and gas is being pulled off of the red giant and spiraling around the white dwarf into what's called an accretion disk. And one of the things I don't think we mentioned yet is that what often happens in an accretion disk is there's also material that tends to flow outward out of like the north and south pole, the magnetic poles of this disk. So think of like a vinyl record or a CD or something as this flat disk of gas, but flowing out from the middle up and down is gas. And I think that's what's making these emission lines, is that right?
Yeah. That's what we're getting from here.
Yeah, so they're jets of gas being flung out into space.
And this is a variable star, so this also has this also changes its brightness and changes its spectrum. So it's a very dynamic system because we've got two stars having fun together. Yeah. Okay. We've hit the zoom limit once again.
Yeah.
So I think we'll do another round of this, and I'll switch target from CH Cygni to a blue shifted star. So let's do that.
All right.
Okay.
So hang in there, everyone, and we'll take a break.
Just gotta change. Okay, hopefully you can hear me now.
Hey, yes.
Okay, good. All right, let's. I don't know what the. Okay. Okay, let's get back on track.
Okay, we're back.
So you were slewing to another target while we were away, and that is?
It has a name. It's called. Well, this is HFA 751.
Oh.
I think it has a.
Epsilon Andromedae.
Yeah. I think it has a common name. It starts with a T.
Well, it is Epsilon Andromedae. Let's see. Does it have another?
I mean, I have it. Titowin. Titowin. I don't know what that means, but that's this name.
Sure enough.
We need Fred to give us that cultural background.
Yeah. I mean, a lot of them are going to be Arabic or Greek, so.
This is a much closer star than some of the others we've looked at. It's almost 44 light years away.
Yeah. And this is going to be where we talk a little more about redshift and blueshift, because we're going to be calculating that. And hopefully we get something that's reasonably accurate.
So in my reading, to get ready for this tonight, there's two stars in this system, and one of them has 4 planets that have been discovered to orbit around it.
That's interesting.
So Todd is asking about the equipment that you were using. So at some point,
okay, they missed the beginning. That. So let's talk about the beast I have to handle right now. Oh boy.
You're busy. Okay, he's using a CL telescope. Okay, and a.
I don't have the pictures here.
Graph. I wouldn't be able to say a lot about the spectrum.
Well, I'll just. Here's the image. Got him. There's the setup. Well, this is from a year ago, but it's the same setup. This mount, we've got a spectrograph, a C11, dew shield, the monochrome camera, and this is the beast I have to use for right now. So.
Now, do you have more or fewer wires than you had a year ago?
I have much better cable management, so it's less, I guess.
Oh, good job.
Yeah, cable management refers to how do you have all those wires, but not when the telescope moves? How do you keep it from snagging?
I have to thank Doug for that because he introduced me to bungee cords. So
Wow.
so
Well,
bungee
that's
cords are
important for observatories around the world.
Yeah, little bungees.
seen the light of bungee cords.
And the support group. Nice.
Let's get 180. The 3-minute exposure. And while we're that, we'll talk about the star, I guess. Cable management support group. Yeah. So let's. Oh boy, this is kind of a mess, though.
I didn't actually use the word mess. I just asked if there were more or less.
Well, no, it is a mess. This is a mess.
I just wanted to let you know that I didn't say it was a mess.
Well, yeah, this is the pre-bungee cord times, dark times.
A high functioning mess, I would say.
All right, so
Admitting is the first step. Yeah.
we're going to be looking at this system, and there are 2 stars in this system. One is a little M dwarf star. It's actually kind of a long ways off from the main star further in. It's 750 times farther away from that star than Earth is from the sun. So 750 astronomical units out from its main star. And the main star there is an F star in terms of spectral types. So the spectral types are O, B, A, F, G. So F comes before G in that sequence, which means it's a star that's a little bigger, a little hotter than the sun.
Yeah.
It looks like we've
really
got something here.
This really sounds like a run-of-the-mill main sequence star, then, right?
Yeah, it's an F9
Yeah.
star. I mentioned earlier that some planets had been discovered around it.
Yeah.
Through spectroscopy, by the way, and it's not a thing we're going to see. You need to be able to see how the pull of gravity from the planets and the stars very subtly affects and periodically affects the spectral lines. But yeah, that's how they were discovered.
It's actually on that note, it's actually technically possible for the equipment I'm using to be able to detect the exoplanet around the 55 Pegasi. Someone did that with this spectrograph and the C11.
That's awesome.
But I'm not. That's the person who basically invented this spectrograph. So they obviously are much more knowledgeable in how to do that. I'm nowhere near having the skill to do that. But people have managed to do a lot of mind-blowing things with amateur equipment, including an actual detection of an exoplanet. But obviously, this star probably has a less aggressive pull, so it's probably not going to be capable with this instrument. But amateurs have actually been able to do a radial velocity measurements of exoplanets, and it's very common now for amateurs to also do exoplanet transit detections using the dips of brightness. So you hit the star, you measure the brightness over a few hours, and then the exoplanet will cause a dip, and you can actually see that dip using very modest equipment. So,
right, it's when the exoplanet passes in front of the star and it dims the light of the star by 1% or so if you're lucky.
Yeah, I mean, if you have the equipment to do that, if you've got a reasonable camera and you've got tracking and all of that, then you just have to go to one of the finders, like an exoplanet transit finder or other sources, see when a planet's going to transit, be patient and aim at there, then have to learn how to process it. But it's very... Doug has done this twice too, so...
Yeah, well, Vivek showed me how to do that, and I did image or did do a sequence of a star where the exoplanet transit, just like when Mercury transited in front of the sun. What was that, early last year, I think? or was it early this year?
Yeah.
I think last year.
Mercury transit on November 11th, I think.
Oh, okay, of last year, yeah. And we watched it go across. It was a little dot, but if you were doing if you were able to record the brightness of the sun, it would dip a little bit because of that little obstruction, the planet going in front of it. So that's what basically exoplanet um, uh, transiting observation is all about. So when that happens, then you know also, I guess, what the size of the planet is relative to the star and how fast it's orbiting. I imagine there's a lot of data that you can get out of it.
Yeah, it's a really successful technique, and you can learn a lot. And Dave has asked, yeah, spectroscopic detection of exoplanets is based on changes in radial velocity of the star. And with the professional instruments on big telescopes, they can detect changes in the radial velocity nowadays, I think, less than a meter per second. They're getting down to a few centimeters per second. I mean, it's just astonishing, the level of precision that you can get when you have a giant telescope and a good spectrograph on it. Hey, so we have a spectrum here now.
Speaking of radial velocity, we're going to do that now. So
Awesome.
we've got this star. It's a main sequence star, and so we know that this is around 6,563 nanometers, and we know that this, now we can see what the peak absorption here is roughly around 6,562 angstroms. So if you take that difference and plug it into redshift, which is what I'm going to do now, and I'll tell you what the result is. The key thing is we have to particularly subtract out Earth's movement around the sun too, because that induces its own redshift, and you have to correct for that. So
right, people have unfortunately famously discovered planets. When I'll say discovered, I'll put it in quotes, planets orbiting other stars with an orbital period of 365.25 days. Yeah, that means they found the orbital period of Earth. You don't want to do that.
Yeah.
That, in order to calculate it for the star, it's the reason I picked the star, because I used prior software to try to see what the difference is, so I can just subtract that out, and then we can get what we calculate from that. So.
Right, so another comment from Todd about transits and exoplanets and how you can see absorption from a planet's atmosphere. That's right. So you can do a high resolution spectroscopy of a star when a planet is behind the star, and then when the star is in front of the planet, and difference those to determine what the atmosphere of the planet is. And it's not easy to do, but it is doable, and it's better done from space, and I think easier to do in the infrared wavelengths.
Yeah. So, okay, I've got the results. It's a little interesting. So, the raw base width, including, the effect of Earth, is around 50 kilometers per second, and if I subtract out Earth's contribution, then we get around 30 kilometers per second, and this is blue shifted, so this is coming towards us, and the actual radial velocity, I believe, is negative 28.5 kilometers per second. So we're a little bit off. Obviously, this is literally just a 3-minute exposure, and
actually, I think it's 28. So you're only off by 2.
Oh, I know. I said it was 28.
Oh, I thought you said 20.
Well, it's blue shift. Oh yeah, I said 28. Yeah.
Oh, so I mean, I'm impressed.
This is supposed to be due around, if you actually properly calibrate this instrument, it's supposed to do around plus or minus 1 kilometer per second. So.
Okay, so
this is the roughest of calibrations, but it's decent enough.
Right, you're not doing science. We're doing live stuff. It's okay to not be perfect.
So that's how you calculate the movement of these stars. look at the shift, you divide the shift by the wavelength you're looking at, multiply it by the speed of light. There's your velocity. So
So just to double check, the red line there is where the
Rest.
absorption line should be.
Yes.
Is that correct?
Yeah.
And the absorption feature we're seeing is to a smaller number. That's bluer light.
Yeah.
So just the fact that it's on the left side there tells us it's a blue shift. And
Yeah.
then you took away the effect of Earth's orbital motion and calculated how much that was. That's pretty cool.
Yeah, so that's basically how this is calculated. There's also there's going to be some other interferences. If you want to go even more precise, you have to account for Earth's rotation, effects from lunar motion, the effects of the moon on Earth's orbit. There's a lot of more calibration you can do if you want to go even more precise to
Right.
these very, very like getting down to, we need to start looking at the effects of exoplanets. So yeah, calibration's a big part of doing this kind of measurements in general. Okay.
That's very cool though.
I
So
think-
let's see, it's 43.7 light years away, and it'll be here when? Again, that was an attempt at humor, so sorry. And of course, it could have other components to its velocity, right? I mean, it doesn't necessarily mean it's coming straight at us. It could be it's moving at some angle relative to us. Doesn't mean that it's coming here.
Yeah. All right, so I think we can. I'll be changing. We'll just do one last. I guess we're getting closer to the end, so we'll do a few more targets. We won't be able to get to all of them, but we'll get a few more and then we'll wrap it up.
So where are you headed next, then?
We're going to go to. So on our list we had 3 more stars left. I guess maybe we should pick just 2 of them. So I'll take. Let's see. Let's look at the. I guess we'll look at HD 220825, which is
Okay.
a star. I don't know which.
It's Kappa in Pisces.
Okay, I'll have to. But the thing is, I have to set the spectrograph to a different wavelength. So get that down. So this line over here is hydrogen alpha, and so now I'll have to change it to something quite different. We're gonna go to the more of the violet part of the spectrum.
The violet part or the violent part?
Yes, to both.
Why not?
Okay.
Okay.
No, it was violet. Yeah, so there go the stars. So this is a star in the constellation of Pisces. It's one that you could see. Its apparent magnitude is about 5, so it's not a bright star. You could see it from Julian for sure. It's 153 light years away, and it's a main sequence star. It's an A star. So they're the spectral types OBA, FG, KM. A is a star that's bigger, hotter than the sun. It's about 2.5 times the mass of the sun, a little bit more than that, and about 30 times the luminosity of our sun. But it's unusual in some ways that we're going to find when we see the spectrum. It's got some cool things.
Yeah, I'm just right now trying to set the stuff up. Okay, so this spectrograph has an achromatic lens, so that means there's going to be some. So the violet part's a little more defocused, so I have to refocus the camera a little bit, and then we'll be ready to make our journey.
Thanks, Todd.
Yeah, okay, now we know when to expect it, okay. Yeah, that was,
Awesome. I'm not going to run the numbers to check your math, so I will assume you was correct.
Check what math? Check what math?
No, never mind.
Oh.
How many years did it take the last star to get here?
Good questions. Okay. It's time to go.
Well, one of the things we've been seeing in the spectrum we've looked at tonight are hydrogen absorption lines, and we saw some others from some other elements that are not as common in stars, but still exist, like calcium and magnesium and things when we saw the reflected spectrum of the sun. But there's some things that you just don't expect to see in the spectrum of a star, but sometimes that's what's there anyway. You get some real surprises, and this is one that has some surprises.
Yeah. Perfect.
This is where we are in the sky.
Yeah, I had to Google the HD number because the hand controller won't accept HD. Okay, we're on our way.
So for the view that we can see right kind of near, you see the target there, but also you can see the square of Pegasus kind of up and to the left of that, and where things are relative to Mars and the moon.
Okay, we're here.
just in line with the moon.
Yeah, they were close together last night, the moon and Mars.
And our target is right in line almost. Yeah.
Yeah.
Rotating variable double star, wow.
Okay, let's see what shows up in the spectra graph. Oh, very convenient. Thank you. Thanks, Mount. That's very convenient.
Wow.
Don't
You done a
just
good
love
job.
it when the star just shows up right bang in the field of view?
Always nice when that happens.
Okay, I'll first take since I moved the spectrum, I'll have to take a calibration spectrum first, so let me get a little quick 30-second calibration.
So once again, he's turning on lamps within the spectrograph to record a spectrum of known sources as a calibration.
Right, which is what, argon gas? And
Argon and neon lamp
mhm.
will show up soon. Yeah, calibration is very important to this line of doing these measurements.
Oh, absolutely.
Yeah. I think we've highlighted before, but it doesn't hurt to stress it again and again.
Right. I mean, otherwise it's just a bunch of lines and you don't really know what they are unless you get lucky and recognize a pattern.
Yeah.
And even then you don't know what it could be telling you because you wouldn't get the red shift or the blue shift or any other kinds of details unless you've done the calibration work.
Okay, let me get the...
And again, this is not something just unique to his equipment. This is what the professional astronomers do too. They have to do this calibration with known sources before they do spectroscopy on the things they want to study in the universe.
Just getting a convenient guide star. Okay.
Good also, yeah. That's we're looking. It's like we're looking through the telescope. But see that right there? That's a little
Yeah.
slit.
Need to get it on the slit.
Gives you the spectrum.
Okay.
That's how we figure.
So close.
That's the thing.
There we are.
It's gotta be going on that.
And you've got a guide star too, so that's good.
Yeah, let's... Okay, we got a spectrum, so I can expose now. This is, since we're going to be trying to look at some really interesting molecules, I'm going to make sure we have a good SNR, so I'm going to take a 5-minute exposure. Yeah, this probably be the last star for the party.
So what he just said there is he wants good SNR, signal to noise. Is that really what you're after here?
Yes, signal to noise ratio, yeah.
Yeah. I'm just trying to make sure we're translating for everyone.
Yeah, because if you notice the noise, it appears as you know, just noise, and you get these squiggles. And since we're looking at a spectrum, we want very clean. Since we're going to be trying to look at some isolated lines, we want to be able to separate an actual signal from an actual absorption or spectral line from just random noise from the various sources. So
right,
by taking more time to get the light, you get more signals, so you can overcome the noise. Okay, so how much? So
if anyone that's tried to take a picture without a flash on their phone in low level light has seen the effect of not having good signal and having a lot of noise. And you're just boosting this by getting a better signal by doing a longer exposure when you get enough light. Everyone needs to remember that we saw the star and the star looked bright, but we're taking that light and we're spreading that light out, and we're effectively lowering its brightness by doing that. So a longer exposure gives you more light to be able to see what it is that you want.
So Vijay Kumar asked, how much of the internal core can be studied? So I assume that's of the star. So that's pretty difficult to do because you're not really seeing that directly. But there's a different techniques for being able to study the core of a star, especially if it's the sun. So you can have astroseismology, if that's
right.
Astroseismology. It's
right.
differently, but that's trying to study the structure of a star by looking at all of these pulsations and trying to use that to look into the core. We do a similar process when we're trying to study the Earth's core. So an earthquake, if it happens on the surface, those waves can go through the Earth's core itself. So we can use that in order to look at we can use that to be able to see how the core of the Earth or a star, how it affects those vibrations and what happens to that. So that's a technique to be able to understand, to understand stellar structure, but it's obviously a pretty hard thing to do, and it's something we're still trying to get to better understand.
Right, and we match that up with mathematical models of the interior, and the dynamics and the temperature and the pressure and the flow of radiation through a star. All of those help us to learn about the inside, even though we cannot directly see it. We think that in basic principles, we have a good idea of what's really happening in the core of a lot of stars, what type of fusion is happening and at what rates. But that's because we've had these mathematical models that sort of build the star up mathematically, and we can match that to what we see on the outside. So how are we doing here on the spectrum?
We're 250.
We're okay.
We're 50 seconds left. Yeah, that's the reason this is going to be the last star for the evening.
Yeah. Well, that's good, because there are surprising things in this star spectrum.
People may also wonder what kind of energy source Vivek is using to be doing running all this technology and keep it going for 2 hours. Of course, the 2 hours is after thermal preparation.
Right. So how early did you get set up tonight?
Well, this setup has been outside for a few days, so I haven't had to build it from scratch. I just had to take off the dust cap and put in a camera and get all of the streaming stuff ready. But yeah, if I had to set up everything from scratch, this would be a lot more of a dumpster fire than.
I wasn't going to say that there was anything tonight that resembled a dumpster fire, but maybe we should poll the audience instead.
Yeah.
No, we appreciate that you got this great equipment that you're sharing with everybody and showing us something that most people never, ever get a chance to see.
Yeah, this was a little ambitious from the start because, you know, being able to, because there's a lot of preparation and a lot of work to handle this kind of big, get some good results. But glad it's worked out. The only thing we have to figure out is how to get on Zoom's better side.
Well, maybe we better shell out a little bit, maybe for a upgraded Zoom. But we thought we were good for a couple hours because every one of these so far we haven't had any time limit. But anyway,
it's a bit strange about this time limit stuff, but you make do with what you got.
Yeah.
Right.
This is actually the first time it's done that. So that's it. Oh boy.
Well, I'm glad Todd's enjoying it.
Yeah. Gotta get a sniff of that. Alright. Oh, here we go. It's okay, we're gonna end soon, so not a big deal. Alright. Now I'm trying to match up all of these spectrums with what I'm looking at right now.
So earlier I had mentioned that stars were basically just hydrogen and helium with small percentages of other elements. And the elements that are really common that we see in Earth, we see in the spectrum of the sun. And then that includes carbon and iron and some things. But certain elements across the universe are really rare and very rarely seen in stars. And you might be seeing some of those in the spectrum of this star.
I can get the... Alright, please. Well, this is the worst time to realize you made a mistake. I entered the wrong wavelength. Shame on me. Alright, let's try this again.
So it's not quite spitting out what you expected then?
No, I typed something wrong and I entered it, and then I realized I typed it wrong. So I have to retype it again.
Don't worry, no one is judging you based on your typing. Much.
Not much, hopefully.
Right.
Try this again. 493.317. All right. Okay.
Let's see what we get.
That's that. Okay. Now I'll get it right for now. 47. I'm basically matching what it identified as a peak with what that corresponds on the lamp. That's the procedure.
Okay.
Okay. Got it right now. And yeah, linear, so it's got it right. Okay. We'll get it from now. And Oh, it's got a lot of elements in here now. Interesting.
So, is that emission or is that blackbody curve?
That's wrong. That's what it is.
That's why it didn't look right to me.
All right, we'll go back to backup plan and we'll try to identify based on that. Always got to have a last minute problem, of course. Okay, let's get this. Last minute problems are us. Okay, that's more reasonable.
Oh, okay.
All right, let's. Okay, in order to understand what we're actually looking at, we're gonna have to get some reference. So let's get some old data. Yep, wrong place. A to C.
All right, so be patient, everyone.
This is right. Okay. Time to compare this star to this star now. Please load. Alright. Let's take a look at what this is. So, here's an example taken earlier. So this is a similar star. These are called chemically peculiar stars. So we've got a lot of strange elements here. So you can see this star in particular has some europium, chromium, hydrogen. This is a hydrogen-Balmer line. We've got silicon, strontium. This is the strontium line over here. We've got chromium and some manganese lines, and you can see them over here. And these are corresponding with the absorption lines. So we've got, this star has a few of those. Now, when I was talking about signal to noise ratio earlier, I meant it because we've got some noise here, but I think we can get some good information out of this. So according to prior research on the star, we should be able to see some chromium, strontium, and europium. So let's start hunting for them. Okay, let's see. Strontium is around 4,200. Okay, I think it figured it out. Yeah.
Trick is that the one you just took doesn't have your wavelength on it, huh?
It doesn't have, because the thing that does wavelength calibration is a script, and the script did an oops.
Was not nice to you.
So I'm just gonna try to. This is now the time for pattern recognition. So
yeah, and don't worry, there's only 3 minutes and 40 seconds left. No pressure.
Okay.
Yeah.
So this actually matches. Okay, that makes a lot.
There you go. Yeah.
Okay, this one is, so let's see, what's the cyan? Cyan's, okay, got it. We've got a combination of europium and europium. We got a europium line right here. This is an absorption line from europium. So if you don't know what europium is, it's radioactive. It's a heavy isotope. It's used a lot for paints, for fluorescent paints, and it's a pretty exotic metal for stars. But somehow this star got its hands on some europium. So this absorption line roughly corresponds to europium.
Well, maybe it was formed out of a major supernova, or in the neighborhood where there was one.
Yeah, there's a lot of different reasons we could for getting that. So this other pair over here we have, this one corresponds to where strontium would be. So strontium is it's a transition metal, I think. Of course, this is not. I wonder if you were a professional astronomer, you wouldn't call this a detection because it's pretty noisy, but I think it's somewhere there.
Fair enough.
I mean, this kind of spectrum you take hours of data to get, so we're kind of on the fly here. But this is.
Go ahead.
But what we got here, this one's pretty strong, I think. This is chromium. This is something. So this is the other line we're talking about, chromium, and chromium's it's another transition metal. So we're seeing, and you tend to see a lot of metallic lines in this region of around pretty much violet. So if you look at the synthesized spectrum, around 4200 to 4500. So we're violet, blue, shorter wavelength territory. But this is where you see a lot of interesting metal lines.
And this is very unusual because, I mean, europium, strontium, chromium, these are not elements that are really high in abundance throughout the universe. Yeah, it's kind of surprising to see them.
Yeah. So that's why we call these chemically peculiar stars, because they are chemically peculiar. We've got some. There's some stars that have holmium, diprosium, some rare earth metals.
Right. So Zoom is saying we have less than a minute.
Yeah.
Okay, we want to reconvene, or we want
to? Or do you want to? I guess
call it a night, since it's been over 2 hours already now.
Yeah, I guess we'll do that then.
Okay. Well, hey, I just want to thank you, Scott, for joining us tonight. You know, I may on a little bit made a stellar contribution.
Oh.
And
thank you.
You know, we're hoping to be able to join us again. I'm not sure what we're going to be doing in the winter season. We're definitely going to aim at doing some more. Weather will probably determine.
Let me try that again. Let's try that again.
I'm back, I think. Can you hear me?
Yeah.
Okay. Yeah. Well, and I also want to thank everyone who joined us. For people who joined in late, this is Doug Salsi, Vivek Vijay Kumar, and Scott Cardell, who is an associate professor of astronomy at Palomar College. And please feel free to subscribe to our channel. That way you will be notified whenever we do the next star party. And send us a comment at juliandarksky.network@gmail.com, and we will add you to our contact list, and we'll notify you by email when we get on the road again. Also, Curiosity Peak Observatory, check that website out. It's where we do our astronomy in Julian, and you can also email us there at curiositypeak@gmail.com. Okay. Anyway, thanks, Vivek.
Yeah.
Good night, and I think we got a lot of science out there.
Yeah, we had some troubles, but we had some troubles with Zoom and all, but I think we've done a decent enough job for that.
Yeah. Okay. All right. So everybody have a good weekend and stay safe and keep looking up.
Yeah.